afternoon to all. Today I would like to discuss how the graphic processing unit is used for parallel programming. The contents which we will consider is why parallel programming is needed, what's the Flyn's taxonomy, how parallel computing is to be taken place, and hardware platform of multi-core GPU computing as well as a programming help in the form of CUDA. Why parallel programming is needed? Because the traditional sequential computing has reached its limitations. Further, we cannot explore either its hardware form or software form. The parallel is the way of seeing how to optimize the resource utilization, how to get better return on investment, and also, of course, improve the speed of computing. The Flyn's taxonomy has categorized the architectures broadly based on instruction stream and data stream. There are 4 such classifications are presented: SISD, SIMD, MISD, and MIMD. SISD is a single instruction, single data stream. SIMD, single instruction, multiple data stream. MISD, multiple instruction, single data stream. And MIMD is multiple instruction, multiple data stream. Among them, SIMD and MIMD are used for parallel programming. Okay, the parallel programming is focused on how single instruction can be used to perform on different data items with the same operation. SIMD, single instruction, multiple. The first ever explored parallel approach is ILP, instruction level parallelism. Of course, it has its limitations of the dependencies that are available in instruction. Indeed, it's a fine-grained parallelism where we can explore resources effectively. Later, it has gone for threading, then hyper-threading, multi-threading, and whatnot, multi-core, and so on. As the number of processors are increasing, the cost of implementation is also very increasing. In this era, the graphic processing unit, which was used originally for improving the quality of picture, can also be utilized for general purpose computing. Hence, they termed it as GPU, general purpose graphic processing unit. And the trend is maximizing the GPU utilization for computing, and it is resulted era of HPC, high performance computing. Instead of depend on costly single mainframe server, we can use the small existing hardware resources for effective computing. Recognizing these potential performance gains, the people, developers, and everyone want to utilize the GPU. Of course, we need a programming support, an application programming interface, how to use this GPU. Indeed, the NVIDIA has provided the support in the form of CUDA, Common Unified Device Architecture, which supports any parallel computing platform and provide programming language support to the user. It allows the creation of a vast number of threads and make them to run on stream multiprocessors, and each stream multiprocessor internally containing the computational units. The logic computation on GPU is on stream processors, where the data is diverted to several stream processors which operate on the same instruction using graphical memory. Of course, in order to make it to work, it is required to transfer the contents of main memory to the device level and vice versa. This was done with the CUDA preliminary instructions such as to device, from device, etc. We are going to see in one sample programming that the graphic block scheduler, instruction cache, and wrapping instructions, and so on. All we have seen a 64 KB register file is used, etc. And each switching processor is containing the floating point functional units, multiplication units, ALUs, etc. A simple ZPU can have 240 cores and it can extend any number. The program is subjected to compiler, which is using NVCC, that is separating the high-level program instructions that are to be done at CPU level and kernel instructions that are to be considered on the device. The CUDA compiler is able to generate object file, and both object files are linking, and it is running both CPU as well as GPU. Threads are the basic units, and how to have the thread states, thread organization, blocks, grids, and how to decide how many number of threads are required, all will come based on the problem and how you are organizing the threads. Threads can be simply divided into a two-dimensional approach called as blocks. Each block will have X as well as Y as a coordinator. This is a sample to 64 threads are distributed among 2 rows and 3 columns, etc. Each block is further divided and thread numbers are given. These are the thread numbers for block 1, 1, thread 0, 0, thread 1, 0, thread 1, 2, 0, thread 3, 0, and so on. So total 12 threads have been distributed here. Indeed, we can organize the threads even as grids, a three-dimensional approach. Multiple grids are to be formed as a cube. Each grid will have a set of blocks and each block will have a set of threads. And how to compute the thread number, and that depends on the ID of a grid, block ID, and the concerned row as well as column ID. For example, the 12 threads are numbered in the block 1, 1 is like this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc. 12 threads will be numbered like this. In CUDA, the host and devices have to separate memory spaces. Variables have to be moved from one space to another space. And the instructions that are supported by the CUDA is CUDA memory copy from host to device, CUDA memory copy from device to host, etc. This simple program is adding two vectors, where vectors are defined at CPU and processing is taking place at GPU. And a kernel function which will work at GPU is called with add, and it is telling there are n threads are there organized in one dimension, and the three variables, three arrays A, B, and C are sent to the device. After performing the operation, that is addition, here it is simply saying AI equal to BI plus CI, and the results are to be sent back to the CPU. And of course, once program is over, we can free the memory space occupied by these arrays at the device level and at the processor level by the free command.